We've looked at liquid as a condensed phase and the property of vapor pressure we've spent a lot of time on, but I would also like to look at some more properties of liquids. Some terms that come up are cohesive forces and adhesive forces. These are macro scale descriptions of what are essentially intermolecular forces within the substance and between the substance and the walls of the container the liquid is found in. So, cohesive forces are a sum of attractive forces within the liquid. Within, say, water, there's hydrogen bonding, and if you think of the macro scale net attractive forces within the water, we call these cohesive forces. Adhesive forces would be between the liquid and a solid surface. So if a glass container holds water, there's attractive forces between the glass and the water. Those are adhesive forces. So one property is surface tension, and we see in this figure on the left a picture of molecules, uh, or a conceptual picture of molecules within the water, illustrating that water in the interior of the water has intermolecular force interactions with neighboring molecules in all directions. But at the surface of the liquid, there is a lack of this intermolecular force in all directions because the molecules at the surface. And this causes a surface of a liquid to act as almost a very thin membrane. Uh, the molecules form this thin membrane at the surface that is somewhat difficult, in relatively speaking, to penetrate. So when you see an object or like a bug walking on water, it's able to take advantage of surface tension, creating this thin membrane. Another manifestation of surface tension is droplets. So a droplet forms because we have cohesive forces within the liquid, adhesive forces causing a surface tension, and the nature of that surface tension is for the water molecules to want, or whatever liquid it is, to want to minimize the surface area. Uh, the more molecules that can experience full intermolecular force interactions in all directions, the lower the energy. So the water will try to minimize a situation where molecules are at the surface, and forming a sphere would do so. Uh, and so we can see this picture in the lower right where we have different substances like mercury and water. They have a high surface tension and they form spheres on the surface. But acetone has a very low surface tension in comparison, and that liquid tends to spread out. The surface tension isn't high, so the liquid does not pull itself into a sphere as readily as the other liquids with a greater surface tension. This is one way you can measure surface tension, is by measuring the angle, uh, the contact angle of the droplet on the surface. The formation of these droplets is due to the surface tension of the liquid, but it also has to do with the material that the droplet is on. So, for instance, a waxy surface on a plant is nonpolar, very different than the very polar environment within water with all of its hydrogen bonding. So, water is not very attracted. The attractive forces between water and that waxy surface are not favorable. So that's going to help to form these spheres, these droplets. If you have a surface where the water is more attracted to the material, then perhaps the contact angle will not be as great. That's just another variable. The surface tension values in joules per meter squared for several substances are shown here. And so we have a trend in boiling points which truly indicate the relative strengths of intermolecular forces. So mercury has the highest, followed by octane, and then water, and chloroform. If we look at the trend for surface tension, mercury is the highest, but then water is higher than octane, so it's not the same order. So it turns out that there's not the correlation of surface tension and intermolecular forces is not as good as that of the boiling point, but generally the stronger the intermolecular forces, the greater the surface tension. The same holds true with viscosity. We don't see a very strong correlation. What is viscosity? It's a measure of a liquid's resistance to flow. So when you think of honey being thick compared to water, the honey is viscous. So the higher the viscosity, the slower that it flows. So if you look at this table, glycerol has a very strong or very high viscosity. Water's viscosity is not very strong in comparison to glycerol, and water and glycerol both have hydrogen bonding. Glycerol is a larger molecule with 3 OHs on it, and so in that regard, the strong hydrogen bonding intermolecular force may play a role in the viscosity of glycerol compared to water. But in general, the trend is not a good measure of intermolecular forces. As a matter of fact, another known variable is that long molecules have a higher viscosity. So as you make molecules longer and longer, if they're in the liquid phase, they may result in a viscous liquid because the long molecules might wrap around one another and have a more difficult time sliding past one another. Capillary action is another phenomenon related to adhesive and cohesive forces. So capillary action is what happens when you, say, dip a paper towel into some water and the water climbs the paper. The liquid is defying gravity. Well, this is due to the relative strength of adhesive forces and cohesive forces. So paper is made up of carbohydrates, which have a lot of hydrogen bonding, and that's a very favorable interaction with water. So there's some adhesive forces between the paper and the water that are favorable, and the water is attracted to the paper. If we look at mercury versus water in glass, I should note this is glass tubing here, we can see a difference in the capillary action. Water, when you place it in this glass tube, you start with a meniscus here at the starting level of the water. As you insert the tube, you notice that the water climbs up the tube, and that is due to the adhesive forces being greater than the cohesive. So the adhesive forces are the attraction between the glass, which is polar, and water. It's between them. The cohesive forces are between water and itself. It's a very favorable interaction between water and glass. For mercury, the cohesive forces are greater than the adhesive. And as a matter of fact, mercury is a nonpolar liquid, and it will not have a favorable attraction to the polar surface of the glass. So the mercury sort of pulls away from the glass, and you might see that the level in the tube dips. If you looked closely at these pictures, you saw the curvature of the liquid in the tubes. That's called a meniscus, and that's the same phenomenon. At the top of the liquid in the tube, we see the curvature of water. Its meniscus is concave, and that's for the same reason we have capillary action in the glass tube. The water is attracted to the surface of the glass, and it climbs up on the sides. In the middle, it's not touching the glass, so we get this curved up shaped concave meniscus. Mercury, though, is not attracted to the glass. It's very different. It's nonpolar, and so in a way it's repulsed by the surface, and you see the meniscus curves downward. So we often think in terms of, water and glass are both polar. The water likes the glass, the mercury doesn't like the glass, but try not to anthropomorphize these chemicals. It's not like there's truly a desire to be with the glass or to get away from the glass, but like dissolves like, we sometimes say, like two polar liquids will dissolve in one another, but a polar and a nonpolar do not. Or in this case, the water likes the glass. But it's truly about intermolecular forces, favorable interactions, and non-favorable interactions. So to summarize the properties we've looked at for liquids, as the intermolecular force strength increases, the enthalpy of vaporization increases, and so the vapor pressure decreases. The normal boiling point increases. The surface tension increases, but it's not as precise of a correlation, and really it's not a good correlation for viscosity, but in some cases there can be a little bit of correlation. So we saw glycerol versus water, both have hydrogen bonding. The glycerol is more viscous, probably because it has more hydrogen bonding. It's also a longer molecule. That's another variable. So